Hi, this is Bilal Arslan, the captain of the Suas Anadolu team of Anadolu University. I am a 4th grade computer engineering student. I have been a part of the team and involved in unmanned air systems for 3 years. I am responsible for leading development and testing progresses of our UAS named Markut. Additionally, I have developed the onboard computer systems for imagery.
Hi, this is Derya Kepenek. I am a 3rd grade student in Material Science and Engineering department. I have been in UAS technologies for 2 years and I have been managing our autopilot system for a year and a half. I am responsible for integration, installation and calibration of our autopilot system and its components. Moreover, on the flight line, I will prepare the flight plans and check instantaneous condition of our UAS.
Hi, this is Hasan Mertcan Özkan. I'm a 2nd year student in Electrical and Electronic Engineering department. I have been in the team for a year and a half. I work on aircraft structure, electrical systems and autopilot systems. During flights, I control the current status of the UAS.
Hi, this is Mustafa Gökçe. I'm 4th grade Electrical and Electronics Engineering student in Anadolu University. And I am a member of a team almost for a year. I am responsible for obstacle avoidance performance and wireless telemetry communications.
Hi, this is Oktay Kırık. I am a 4th year computer engineering student. I am in the team for a year and a half and I have been interested in air systems since my 2nd year at the university. My role in the team is providing communication between UAS and the GCS computers and I will be maintaining the interoperability server.
Hi, this is Alperen Kırmer. I'm a 3rd year computer engineering student and this is my 2nd year with the team. My responsibilities are building the image processing algorithm and operating the image processing user interface during the flight.
Hi, this is Nevzat Çırak. I am the 4th grade Electrical and Electronics Engineering student. I am a member of the team for 2 years. I participate in image processing part of the team. I am working on optical character recognition. On the flight line, I'll deal with image processing.
Hi, this is Musra. I'm a 2nd grade Material Science and Engineering student. I have been a part of the team and care about unmanned air systems technologies for 2 years. I am interested in structural part of aircraft. My responsibilities are doing pre-flight, flight and post-flight checklist. And I take note some problems which may happen during the flight tests.
Hi, this is Kadir Çelik. I am a 2nd year student in avionics department. I have been working on manual aerial system for 4 years. I am a member of team for 2 years. My first task is to provide maintenance and make our aircraft airworthiness, and I am responsible for the full run the engine, make the final check before the flight.
Hi, this is Görkem Kısıkkaya. I am a 3rd grade student in Electrical Electronic Engineering department. I have been on the team from August and I have 1 year experience of UAS technologies. My role is producing image processing targets and the simulating of the competition area with Google Earth.
We have chosen a fixed-wing conventional tail Phoenix Trainer 60 as an aircraft. To complete each mission tasks, several subsystems were designed and placed on the UAS, specifically autopilot, imagery, communication, and air delivery subsystems. These subsystems consist of several hardware and software components such as Pix-Hawk autopilot system for autonomous flight, camera and onboard computer for imagery, long-range antennas for communication, and triggering and safety mechanism for air delivery. This year, we will attempt autonomous flight, object detection, classification and localization, air delivery, and stationary obstacle avoidance. We are very confident with autonomous flight, ODCL and air delivery. However, we are not sure about stationary obstacle avoidance because it is still being developed and we have not tested it yet. We will not attempt the off-axis target because of the capabilities of the aircraft and also moving obstacle avoidance task because of updating the flight route while airborne might be risky and our algorithm not optimized for determining that kind of operation.
The simple model was adapted for development of the UAS. Up to now, 3 prototypes have been built and tested. For each prototype, we first applied unit testing on the ground. And if the component passed the test, it is integrated in the UAS. Then performed compatibility tests on the whole system. After being sure all subsystems working well altogether, the flight tests were performed to see if the result meet the requirements of the mission tasks. Up to now, over 50 flights were performed. During these flights, in the most of the cases, flights were performed autonomous mode. However, during the takeoff, landing, and emergency phases, the safety pilot takes the control back for only 5 minutes for each flight. After analyzing the specifications and capabilities of the aircraft, the pilot system was tuned to improve the performance and stability of the autonomous flight, takeoff, and landing by using additional sensors such as rangefinder and airspeed sensor. During tests, there is more than 90% of waypoint accuracy in moderate weather conditions, and there were a great number of waypoints attempted. We are very happy with the waypoint capture ratio, which are most of the cases over 90% accuracy. In fact, as long as the radius of successive waypoints do not intersect with each other, we won't miss waypoints. Therefore, we see too small amount of waypoints, such as 10%, were missing as long as the weather conditions are good. We programmed a Python script to create an optimal flight path to avoid obstacles. With many geometrical and logical operations, algorithm decided the shortest, least turn, non-obstacle path for our UAS. This part is critical for safety and still under development. We are trying to prepare and we will test it soon.
So far, we have taken more than 3,000 images. The imaging performance was enhanced by optimizing the settings of the camera. While the UAS fly at a cruise speed, about 17 meters per second, we use 1 frame per second capture rate to scan the whole search area with a slight overlap. However, the transmission ratio from the UAS to the ground station is 1 image per second. In order to minimize the transmission time, the image quality is reduced. The resolution of the target images depend on target size and altitude, but we can say that there is an average of 150 by 150 pixels resolution, which is sufficient for image processing. During the development of the image processing algorithm, we have used the images taken at 2015 competition, and we also took extra images in our test flights. The algorithm is tested with 10 targets, including the emergent target. The detection algorithm hasn't missed any of the targets. However, there is also a high false detection rate. We are able to eliminate the false detections with a post-processing for the classification. Classification depends on many parameters, including the brightness or the quality of the image. However, for our test data, we are able to obtain an 80% accuracy for classification and 60% accuracy for localization. The first step was testing whether the parachute is working properly. We also wanted to make sure that the parachute protects the payload. To try this, the parachute was released at low altitude from hand more than 50 times, and about 95% success rate was obtained. Then we have integrated the drop mechanism into the aircraft to observe if it is working correctly. We updated it a few times to solve various problems. We have observed that the payload lands about 90 feet away from the drop location. We're still working on it to reduce the distance.
To perform full mission test, the competition area was simulated in a safety place in Eskişehir. During these tests, we built different scenarios for waypoints, search area, targets, and air delivery geolocation. The mission time starts when the flight data is streamed to the interoperability server. The aircraft takeoffs and starts the waypoint capture mission. After capturing the last waypoint, the aircraft enters the search area and imaging system initializes. The captured images are transferred to the ground control station automatically, and the image process computer processes the image. Whenever a target is found, the result is automatically sent to the interoperability server. For the air delivery mission, the autopilot triggers the mechanism and releases the payload on a given geolocation. After completing the missions, the aircraft lands. The results show that the UAS was capable to complete the autonomous flight, ODCL, and air delivery mission tasks successfully. During these tests, we had some problems with imaging system and monitoring flight data due to the signal loss. To correct these problems, the telemetry module was changed with an improved one and the imaging data link antenna positions was changed. The table shows the last 5 full mission test results. As an expected result, we might get approximately 70% score in the mission demonstration section.